And I'm live. Excellent. And a cheer goes up across the town of Barnegat. A cheer that I can audibly hear from all of you now that you can hear my voice. It's so wonderful. I don't know. I'm sitting on my computer right now, and I am trying to upload a couple of PDFs that we are going to utilize today. I will explain what's going on with those in a few moments once I get the correct files. And there we are. Okay. I'm not going to click to upload them just yet. I'm just going to have them ready to go. PDFs for today. There we go. But yes, I'm giving people a few moments to get in to the live stream. Looks about 13, 14 people or something like that getting into that live stream today. There should be more in a few moments. Obviously, you had an assessment due today. I just checked it probably a few minutes ago. Let me double check it again. I want to say the vast majority, yep, there it is. The vast majority had turned it in. My hope and goal is to have that graded before I leave the building today. That would be ideal in this situation. But if you haven't gotten that done, it was due about 24 minutes ago or something along those lines. Anyway, as for today, this week is dedicated solely to reviewing for said midterm. Now, I have several things in mind for reviewing for the midterm, but just some pieces of information that you need to be aware of. First of all, your midterm is scheduled for Tuesday, the 26th. That is the period 1B, 2B midterm day, Tuesday, the 26th. Now, supposedly, you guys should be back in my classroom. And I say supposedly because, I don't know, every shutdown that we've had has felt like they've done it at the last minute. And as a result, I mean, yeah, you guys are supposed to be coming back next week. Yeah, I'll believe it when I see it. And then when it happens, I'll probably be like, all right, what changed? Nothing. Okay. All right. Oh, our region in New Jersey has the worst numbers in the state and they haven't improved. Cool. All right. Yeah, but let's all get back into the building. So anyway, Tuesday the 26th is your midterm. Now, the schedule, I believe the principal should have sent out the schedule, like the time schedule for it, either at some point, either yesterday, this week, whatever, I don't care. But my goal for today and Friday is to review for said midterm. And as I said, I have several things lined up. Number one, I have a bunch of free response questions that we are going to go over as a group today. I'm going to be posting the problems and the answers PDF so that you have them. I would suggest not utilizing the answers PDF until you've given the problems a try. That would be ideal. Simply because you can kind of like test yourself as, okay, how did I handle the situation? Now let me compare it to the ideal situation. I've only have the answers. I didn't actually include any of the scoring with it. So I only included the ideal answers. Keep that in mind. As for Friday, obviously, I don't think that we're going to be able to get through every single of my free response questions today. So whatever we don't get through today, I would like to finish up on Friday. I also have a separate practice quizzes that I would like you guys to try, but I'm not going to utilize class time to get that done. Now, again, I emphasize the fact that it is a practice quizzes. It is not a quizzes that is going to count against you. I'm going to assign that before I leave the building here today. It's a bunch of questions that are specifically designed for the midterm, but they're multiple choice questions, obviously. The intent of me assigning them outside of class, I would like them to be done before Friday so that when we come in on Friday, I can then look at the report on quizzes and be like, okay, these are the questions that we need to review. That's what I would like to do. So to recap for those of you coming in or who have just made it in, number one, your midterm is on Tuesday. First one, period 1B. Well, Tuesday, second day, whatever. Don't care. We are going to be reviewing free response questions, which I'm going to be posting into the Google Classroom stream in a few minutes. Whatever we don't finish, we're going to finish on Friday. I am also going to be assigning you a practice multiple choice quizzes. So I can look at that data and know, okay, these are the questions we need to go over, and we'll go over those on Friday. So while I go post the problems that we're going to be working on today, I'm going to ask all of you lovely people to leave a comment in the chat, just so I can see what the heck's going on and who's here, and that would be fantastic. So please do that now while I post the sucker. Let's see. Post. And posted. Excellent. So in the Google Classroom stream, there should be two PDFs that say midterm review. One of them says problems and the other one says answers. For the time being, please only utilize the one that says problems. Obviously, whatever problems we don't get to, we can always finish them on Friday. But whatever you choose to do on your free time of reviewing, whatever you do there, you at least have the answers to work with. And that would, sorry. I'm trying to get the chat up on my phone, and I just did that, but my volume was up. Nailed it. There it is. I can see all of your lovely hears. Here. Okay. So I'm going to flip over my screen. And again, just for the sake of argument, in your Google Classroom, there are the PDFs for today. Please utilize the one that says Problems 2021, and that's the one that we're going to use. Now, what I'm going to do, I printed out a copy, and I have that copy right here. And just so you know the structure of this thing, just so we're all on the same page, the way that I did this was just a pure cut and paste job. So for example, the first question on the problems PDF, it says 2002 AP Stat free response questions, numbers 2 and 3. And then on the next page, it says 2001, number 1. I put these questions just as a pure cut and paste job just because I wanted to have a very easy review to go over with you with certain types of problems. Now, on the answers PDF, on the PDF that says answers, the answers are in the exact order that they're in on the problems, and they're labeled as such. For example, here are the scoring guidelines for 2002, question 2. Oh, and here are the scoring guidelines for 2002, question 3. And then it jumps back to 2001, question 1. They are in that particular order, and that is how they are organized. They are organized by the year that the test was taken and the problem number that they were on that particular test. I just wanted to make sure we were all on the same page before I began reviewing these questions. Now, for your sake, what are you to do while I am working through these problems? I would suggest that as I am working through these problems, you take whatever notes or statements or jot down any little piece of information that you feel may be important as we are reviewing these problems. Perhaps there's something that, oh crap, I need to go look up this and study this more, or oh, I need to find another question in regards to this in order to get extra practice, or something along those lines. Finally, before I begin going over these problems, just for the sake of argument, I am going to include, and you can see this on the board, I am going to include on your midterm the formula sheet. I'm going to make the formula sheet available to you. Any of these formulas are fair game that are given to you, obviously. The third page isn't something that we've gotten to yet, except on the third page, they do give you this interesting thing right here. And what this fraction is the calculation of a z-score. It's very strange. But the rest of this we haven't actually gotten to yet. We've gotten up to this formula right here in regards to the binomial distribution. These are expected values. This is basic probability stuff. And there is linear regression formulas that they give you as well in terms of calculating the slope and the y-intercept. Just for the sake of argument, they give that to everybody on the AP test. They typically haven't changed that thing in 20 years. Wow. Okay. Let's start with 2002, number 2. I'm going to zoom in on this, and I'm going to talk about what I find to be very important with this problem. And of course, if you can't see it that well on the screen, I provided the PDFs for you in Google Classroom. Here we go. A manufacturer of boots plans to conduct an experiment to compare a new method of waterproofing to the current method. Wow, this problem sounds familiar, as it should. I gave this to you before. The appearance of the boots is not changed by either method. The company recruits 100 volunteers in Seattle, where it rains frequently, to wear the boots as they normally would for 6 months. Okay. At the end of the 6 months, the boots will be returned to the company to be evaluated for water damage. Now, there are multiple ways to answer this question. Multiple ways. The solutions that I gave you on the other PDF are what we call the ideal solution, meaning like, oh, this would be like a perfect score. But there's always wiggle room that you could do. Part A. Describe a design for this experiment that uses the 100 volunteers. Include a few sentences on how it would be implemented. Now, again, there's so many different ways that you could do this particular experiment. See, the thing is, there are some people that, and you probably know what I'm talking about. There are some people that walk heavy. When I say they walk heavy, it has nothing to do with the way that they look. It's the way that their feet hit the ground. Like, for example, I knew a kid in college that every time he walked, his back heel would just slam into the ground first. And you could just, even though he's walking normally, you could hear him walking like from a mile away. It was pretty messed up. And there are some people that are just like very light on their feet, and they just kind of like, you just barely hear them as they scrape by. So in order to have a proper experiment, in order to utilize these 100 volunteers properly, there needs to be a certain level of randomization. There has to be a certain level of randomization. If I'm going to be grading a problem like this, I need to see the proper elements of experimental design. The proper elements of experimental design. There has to be some level of randomization. In fact, in our notes, let me see if I can find this actually. I know in our notes from way back when we were first doing experimental design, I wrote down a bunch of the stuff that we absolutely needed to recognize in creating experiments. Come on, I thought I was almost there. That was chapter 11, samples continued. Unless I accidentally got rid of this page or something along those lines. No, perhaps, did I get rid of these? Maybe I did. Whatever. We'll figure it out later. But let's see how we can do this. One way of doing this problem is with a paired design, a matched pairs design or something along those lines, where one of the boots that a person would be wearing would be, they would perform the new waterproofing method. And the other one, they would just stick with whatever method. So like perhaps it would be, randomly like, okay, your right boot gets the new method and your left boot gets the old method. But the randomization that takes place is randomly selecting which boot gets the new waterproofing method. Another way of potentially doing that is taking the 100 volunteers and randomly splitting them 50 and 50 and having one of the groups have the new waterproofing method and the other group get the current method or the old method or something along those lines. I even read, when we did this response, I even read certain ideas where they would wear one waterproofing method for half the time, like 3 months, and then they would switch to the other method or something. I heard all sorts of crazy, not crazy, I shouldn't say crazy, but interesting ideas as to how to go about doing this. So let's describe a design. So you have 100 volunteers. And now, again, depending on what you want to do, you could split these people up. Yeah, let me split them up like this. I am going to randomly allocate them. I have an idea. I'm going to randomly allocate them 50 and 50. Okay. And I'm going to do a system where one boot gets the new method and the other foot gets the old method. I think that's what I'm going to do. So they would be randomly split 50 and 50. And then I would say, okay, this would be right boot new, left boot old. And then the other one would be right boot old, left boot new, to kind of do that comparison. And again, the reason why I do that is because the way that people walk, I know that there is, some people who like wear out one shoe over the other, or they favor one foot over the other when it comes to walking around. But there has to be that random allocation. Everything's treated approximately the same. Here's the treatment that takes place. And then after the 6 months, you can compare. I ran out of room, but you would compare, and then bring the two of them together and compare. It's perfectly acceptable to create this kind of diagram. I just ran out of room here because I'm trying to fit it in all on this paper. But it's perfectly acceptable to create this type of diagram when doing that, indicating that random allocation, indicating the difference between the groups, and then doing that comparison at the end. Now, for part, hold on, there's an announcement. Frank from Tech. Part B, could your design be double blind? Now, what does it mean to be double blind? To be blinded, there's two ways of blinding. One, the person participating in the experiment does not know what treatment they received. And as a result, yes, they would definitely be blinded to that fact. I mean, if you knew that, okay, my right boot had the new treatment, my left boot had the old treatment, and then that might subconsciously change the way that you walk over the course of 6 months, you need to be blinded to that fact. So it's definitely blinded on that end. But what's the other type of blinding? What would make it a double blind? What would make it a double blind is if the person evaluating the boots did not know what treatment the boot received. Now, perhaps there was some kind of like, something written on the inside of the boot, let's say. I don't know. Perhaps, this was a part of group one, and somebody knows that the right boot got the new one and the left boot got the old one, or the treatments, I should say. But the person doing the evaluating, they shouldn't know which boot got which method. That information is written down, and that information will be known after the fact. But if I'm evaluating the boot, I got to look at that boot and be like, okay, how did it hold up over time? I need to not know what method the boot received. So you could code that on the inside of the boots with like marker or some junk like that, or something, or stitching. I don't know how they actually do it. But yeah, this totally could be double blind. The subjects are blind to the treatment. The evaluator, when that comparison is done, the evaluator is blinded as to which treatment the boot got. So yeah, totally could be. A lot of people missed that the first time we did this problem. Okay. Let's look at number 3. I got to zoom out a little. There we go. There are 4 runners on the new high school team. The team is planning to participate in a race in which each runner runs a mile. The team time is the sum of the individual times for the 4 runners. Okay. Assume that the individual times of the 4 runners are all independent of each other. Always a good thing. The individual times in minutes of the runners in similar races are approximately normally distributed. Ooh, that's good that they tell us that. I mean, that's helpful. The fact that it's normal, they don't have to prove anything. With the following means and standard deviations. Okay. All right. Remember, standard deviation, average deviation from the mean. So like runner 1 on average would deviate by about 0.15 minutes on average. Runner 3 thinks he can run a mile in less than 4.2 minutes in the next race. Is this likely to happen? Ooh, now that's an interesting statement. Ignore all the other runners. Ignore 1, 2, and 4. This is runner 3 by himself. He thinks he can run in less than 4.2. Is it likely to happen? In fact, they're looking for a probability that this would happen. They don't tell you exactly what to do in part A, but the hint was given in the paragraph. The fact that they told you it was approximately normal. The way that you could handle part A here, is you should utilize what we did in chapter 5, which was a normal CDF. A normal CDF will get us there. Now, reminder, normal CDF, they normally, you would do a lower limit, an upper limit, a mean, and a standard deviation. Let me bring it up on my calculator here, actually, because my calculator would have the same setup as yours for the most part. But if you were going to go normal CDF, that would be the order. You'd have to do it in lower limit, upper limit, mean, and standard deviation. So second VARS, normal CDF, you don't use the normal PDF. He thinks he can run it in less than 4.2 minutes, which means, let me go back here real quick. Less than 4.2 would be some small number, like, I don't know, negative a billion, comma 4.2, comma, well, this is runner 3, so 4.5, comma 0.14. That would be sufficient. You could also do this with a z-score, which I'll show you on the calculator in a moment, how you could do the z-score. Let me move that down because it's in the glare. Come on, glare, move out of my way. There we go. So let's see what happens. Click. 4.2, 4.5, 0.14. So we're looking for the probability of him getting 4.2 minutes or less, given that he averages 4.5 with a standard deviation of 0.14. There we go. 0.016. You could also calculate, as I said, a z-score for this guy, and then do the normal CDF with a z-score. Or you could even do, well, maybe you could do the empirical roll. I guess it depends on what the z-score actually ends up being. But it would be data point, minus the mean. I put that in parentheses, divided by the standard deviation. And it gives you the number of standard deviations away from the mean that a data point is. That is the z-score. The z-score. Approximately, well, it's over 2 standard deviations below the mean. Yeah, but I don't think you can do the empirical rule here. So negative 2.14, negative 2.143. I'm just trying to get an approximate number. Let's see, negative 2. Come on. Negative 2.413, or was it 143? It was 143. Come on, 143. There we go. Well, this would be with the mean and standard deviation remains the same. Yeah, it's an approximate number because I rounded the z-score. I like my answer better. 0.016. And that's what it would look like. Then it says the distribution of possible team times is approximately normal. Thank you for telling me that. Now I don't have to actually figure that out. What are the mean and standard deviations of this distribution? Ooh. what the heck do I do here? They tell them, okay, it's normal, independent, that whole thing. They want to know the team mean and the team standard deviation. Oh, I know. I have to combine all of those. All right, let's do it. I can combine all of those. 4.9 plus 4.7 plus 4.5 plus 4.8. Cool. That would be the team average, the team mean, 18.9 minutes, something along those lines. Of course, I would, write down my work for that, of course, but 14.9 minutes is the team mean. Cool. Standard deviation. Well, they're all independent of each other. And to combine the standard deviations, I cannot just add them all up. I am going to have to square them to variance, then add them all up, then square root them back. Let's do it. 0.15 squared plus 0.16 squared plus 0.14 squared plus 0.15 squared. Double checking. Cool. That answer. And then I got to square root that. Square root 0.0902. Cool. There it is. That is the team standard deviation. I'm going to label that with sigma. Sigma team. Or sigma sub t, whatever. 0.3003, I guess, if I wanted to get technical about it. That's how I wrote it down there. I really should do mu t right there. Something along those lines. So this problem is actually combining stuff that we did in chapter 5 with the normal distribution and stuff that we just recently did with random variables. Suppose the team's best time is 18.4 minutes. Okay. What is the probability that the team will beat its own best time in the next race? Well, they said in the previous one, and the team time is approximately normal. To beat 18.4, I would have to have some big negative number, small number, comma 18.4. The team average is 18.9, and the team standard deviation is 0.3003. That is what I would have to do for this problem. Click. Let's clear that. Normal CDF. Small number, comma 18.4. The mean is 18.9. And the standard deviation is approximately 0.3003. There we go. Approximately 0.048. That would be sufficient. Yeah, that would be sufficient to get that problem done. Oh, these problems and the way they do things. Okay. Let's go to the next page. I'm on 2001 now. 2001. Come on, there we go. Excellent. 2001, coincidentally, that was the year that I took the AP stat test. I took it in 11th grade. Anyway, I'm just nostalging, whatever. Number 1. I don't remember this problem, just for the sake of argument. The summary statistics for the number of inches of rainfall in Los Angeles for 117 years, beginning in 1877, are shown below. Okay. One thing I definitely want to point out to you in regards to this problem. We have not and will not use what is known as true mean. It's not something that is taught in high school AP statistics. True mean is something that is taught at the higher levels of statistics if you happen to make it that far. So don't worry about true mean. Okay. Part A. Describe a procedure that uses the summary statistics to determine whether there are outliers. Well, that is just a pure definition, but you could take your definition in one of two directions. One direction that you could take part A, and I'll write this down here, is by describing, and again, it does say describe, so you would have to write out some sentences. I'm not going to write out those sentences today, but I'm saying that you would have to if you were going to do this on an AP test. But you could describe the process of Q1 minus 1.5 IQR, comma, Q3 plus 1.5 IQR. You could describe the process of calculating that and determining that by definition, any data point that lies outside of that range is an outlier. By definition, anything outside of that calculated range would be considered to be an outlier. Now, are there any outliers? Well, we'll deal with that in part B. But part B does say justify it based on what you described in part A. Now, like I said, there is more than one way to actually answer that question. The other way of answering that question, determining any outliers, you could, in theory, talk about unusual data points. By definition, an unusual data point is anything that is more than 2 standard deviations away from the mean. Now, if it were me and they said outliers and they gave me this information, then I would stick with what I've just written there. I would just stick to that and nothing but that. But you could also describe a procedure where it says, well, any data point that is more than 2 standard deviations above or below the mean would also be considered an outlier. By definition, it's technically an unusual data point, but trying to stick with what they got. The reason why I don't like to use why I try to distinguish the two of them, I distinguish the idea of outliers using this and unusual data points using z-scores, is because with z-scores, the assumption is that the data is normally distributed. If you hear z-score, you automatically assume bell curve normal distribution. But there's nothing in this problem that indicated that it was a normal distribution. That's why I don't like that. Now, I'm looking at the scoring guidelines, the solution, and they actually do allow for the fact that you could do z-scores. I'm just saying, personally, I disagree. Because they never said anything about being normally distributed. Whatever. Anyway, let's do this calculation. Are there any outliers in the data? All right, let me do this calculation. This is part B. 9.680 minus 1.5 times the IQR. I never actually calculated the IQR. As a reminder, the IQR is Q3 minus Q1. Q3 minus Q1. And that would be the interquartile range. It is a measure of spread. I will have to talk about CUS in a moment, but I want to finish this problem, but I do want to remind you of CUS. But then the other half of this calculation, plus 1.5 times 9.57. Let me do that calculation real quick right here. 9.68 minus 1.5 times 9.57 gives me negative 4.675. And 19.25 plus 1.5 times 9.57 gives me 33.605. Okay. So this is the range by which you determine whether or not data points in this example are outliers. Clearly, you're not going to have rainfall that's in the negative range. So you clearly don't have to worry about that. The minimum actually on the chart is 4.85, so we're good there. The maximum on that chart, is 38.18. So by definition, according to what I see here, oh wait, 38.18, that's outside this range. Huh, I guess there's one outlier. Well, not exactly. You can't say that there's one outlier. See, this number right here just gives you the maximum number. And I'm going to be very clear with my language, there is at least one outlier. Just because the maximum is 38 doesn't mean it's the only outlier because it's outside this range. There could be a number that's like 37, and that's also outside this range. The best that you can say is that there is at least one outlier. And you can say because the maximum is outside that range. Now, if the minimum also fell into that, which it doesn't, but if the minimum and the maximum were both outside this range, that's a situation where you can say at least two. But since the minimum was within the range, we're fine. It's at least one. Again, you could do the same thing with z-scores, but I don't want to get into those details. Part C. The news media reported that in a particular year, there were only 10 inches of rainfall. Use the information provided to comment on this reported statement. I exaggerated the word only because it was underlined. Part C. Let me line something up right here real quick. Let me line something up just for a visual. The minimum was 4.85. Move that up. Q1 was 9.68. The median was 13.07. Q3 was 19.25. And the maximum was 38.18. The thing that you got to know about the 5-number summary is that each represents a certain percentile. The median is obviously the 50th percentile. Here's the 75th percentile. Here's the 100th percentile. And between each data point lies 25% of the data. It's like 25% of the data is between here. 25% of the data is between here. In fact, boom, right here between these two numbers lie 50% of the data. But now 10 inches of rainfall. 10 inches of rainfall is right there. 10 inches of rainfall falls right in that range. What the heck? There's two ways of talking about this answer. First, well, because this thing is greater than Q3, because 10 inches of rainfall is greater than greater than Q1, I should say. That's within the middle 50%. It's within the middle 50% of data. That's not unusual. It's not an outlier. It's within the normal. It's within the interquartile range between Q1 and Q3. So you could say all of those things to comment on the reported statement. The other thing you could do is also calculate a z-score, which again, I don't agree because they never said anything about being normal, but the scoring guidelines do allow for you to talk about a z-score. So you could calculate a z-score, and that z-score is like negative 0.7 or some junk like that. And because of that, well, it's not unusual. The only way you're on an unusual data point is if you are more than 2 standard deviations away from the mean. But I digress. Okay. Let's talk about the next one here. This thing jumps all the way to 2005. This thing jumps to 2005. Okay. The graphs below display the scores of 32 students on a recent exam. I'll move that up a bit. Of course, you can see this PDF. This is 2005, number 1. Scores on the exam ranged from 64 up to 95, but they don't give you the scores in that thing. They just give you like dots. Okay, part A. Oh, that's right. I wanted to talk about cuss. This is a perfect opportunity, actually, because cuss is in regards to part A, technically. So let's talk about cuss. I want to write something down about cuss, just as a reminder to you all. Zooming out, zooming out. We should already have this written down, of course, in our notes from a while back. But let's talk about cuss. Cuss is the acronym by which you describe distributions. Now, come on, you. I'm going to split my paper a little bit. I shouldn't have split it like that. Whatever, I don't care. Center, unusual. No, I am going to change papers. It's bugging me now that I didn't do this properly. Come on, you. Go away, paper. Cuss. Back to this. Excellent. Now we're good. Now I got what I wanted. Okay. Cuss. Center, unusual features, shape, and spread. That is what cuss stands for. Now, the shape of the distribution, there's a lot of different shapes that you could do, but there are two main shapes that I want to talk about. One of them being symmetric, and one of them being skewed. And the reason why I want to talk about the two, now obviously there's way more shapes than that. I mean, you could also be uniform, you could be unimodal, like there's a whole, unimodal, bimodal, or whatever. There's a whole bunch of different shapes you could be, but these are the two that I want to talk about. Because if your data is symmetric, then you would talk about the center being the mean. But if your data was skewed, then you would talk about your center being the median. There's a clear distinction there. Now, unusual features, either which way you do unusual features, you could talk about gaps, you could talk about outliers, you could talk about peaks, anything like that. That kind of fits into both categories. But then if you're talking about spread, well, if your data is symmetric, then you're going to be talking about standard deviation. But if your data is skewed, then you're going to be talking about IQR, interquartile range. That was a distinction that we made back, I don't even know what chapter we did that. But to describe a distribution, you want to cuss. But depending on the shape, that's going to change the center and the spread that you use. This is just a reminder. Okay, let me go back to this problem now. Zooming in, zooming in, zooming in, zooming in. Here we go. Describe the shape of the distribution. I'm actually going to turn my paper sideways for a moment. There we go. I turned my paper sideways so I could draw that. Looks like a nose, boogers. Anyway, that's skewed. That's definitely skewed. But what direction is it skewed? There's two ways that you could technically be skewed. You could be skewed left, you could be skewed right. This is skewed left. The direction of the skew is wherever the tail is. The data is skewed when there are numbers that kind of pull the average up or down in a certain direction. This one, well, the average is pulling it down because of those numbers down at 64. Like, oh, well, those, if it weren't for those numbers, this thing would have been a bit more symmetric. Yeah, it's pulling them down. This thing is skewed left. Part B. In order to motivate our students, the instructor of the class wants to report that overall the class's performance in the exam was high. What or which summary statistic the mean or the median, should the instructor use to report the overall exam performance was high? Now, here's the deal. The mean, because of the way that this data was skewed, the mean is being pulled downwards. Now, there's two ways of going about this. I mean, you could talk about like, how do you want to motivate your students, or what would make the teacher look good, or something along those lines. What it comes down to is, because the mean is pulled down, you really want to, she wants to report that the performance on the exam was high. So the median is your best bet. The median is your best bet. And you could talk about, well, when they say explain, you could say that, well, the mean was pulled downwards by those lower scores. The median's going to be higher. Be like, look, guys, you didn't do as bad as you thought. Or something along those lines. Part C. The mid-range. Now, the mid-range is not something I've ever taught you. It's not something that's ever really taught. The mid-range is just one of those weird things. But if you notice, they just gave you a definition as to what a mid-range was. The reason why they did that was simply because, they know that you haven't been taught it, but they may do stuff like that. Like, hey guys, here's a random definition that you've never heard before. Now use this definition to answer this question. They'll do that to you. The mid-range is defined as max plus min divided by 2. Compute this value using the data on the preceding page. Preceding page, it's just the data above, whatever. Is the mid-range considered a measure of center or a measure of spread? Okay. Well, it goes from 64 to 95. So, hold on. 64, 95. Let me just see what it is here. 64 plus 95 divided by 2. 79.5 is the mid-range. Is it a measure of center, or is it a measure of spread? And then it says explain. Well, this is a measure of center. This is a measure of center. Now, it's interesting because range in general, when you hear the word range, people typically think spread. When people think interquartile range, they typically think, spread, But this is not what spread is. Spread, like IQR or standard deviation, gives you like an average deviation, or they're attempting to calculate something like that, like an average deviation, how spread out the data is. This 79.5 is basically the average of the max and min. It's the average of the max and min. And because of that, it is more akin to being a center than a spread. Yeah. Anyway, number 2 on the same page. For an upcoming concert, each customer may purchase up to 3 child and 3 adult tickets. Let C be the number of child tickets purchased by a single customer, the probability distribution of the number of child tickets purchased by a single customer is given in the table below. Okay. Child tickets, cool. All right. So if you have no kids, there's 40% of the time there's no kids with the purchase of a ticket. 10% of the time there are 3 kids. Compute the mean and standard deviation of C being the number of child tickets. Okay. This is expected value. I'm going to go to my calculator. Yeah. And I'm typing in the data that I see. There we go. L1 being the number of child tickets purchased, and L2 being the probability of that event happening. I'm going to have to run a 1-var stat. And as we found out in class, the frequency list, we're going to have to type in an L2. Because, L1 is the list, the number of child tickets, and L2 is the chance of that event happening, the frequency list, how frequent it will happen, 40% of the time, 30% of the time, etc. Let's calculate. Oh, interesting. That's really weird that those numbers would just work out so perfectly like that. But yeah, they did. The mean of a child ticket is equal to 1, and the standard deviation of a child ticket is also equal to 1. That is really strange. All right, but that's the way it works. That's what I wrote down. Cool. Part B. Suppose the mean and standard deviation for the number of adult tickets purchased by a single adult are 2 and 1.2 respectively. Oh, sweet, they gave it to you for the adult tickets. All right. Assume that the number of child tickets and adult tickets purchased are independent random variables. Oh, thank God they said independent. Seriously. If they didn't say independent, then there would be a whole bunch of mess where you'd have to justify it being independent, but okay. Compute the mean and standard deviation of the total number of adult and child tickets purchased by a single customer. Oh, it's one of those problems where I got to add them together again. All right, let's do it. I got to add them together. I mean, so the mean combined, I don't even know how to word that, or total. Yeah, let's do total. Mu total is equal to, well, it's 1 and 2, so it's 3. And the standard deviation total, well, I'm going to have to square them and then add them together. 1.2 squared plus 1 squared. Why am I even typing that? Equals that. Square root of 2.44. Cool. 1.562. 1.562. Nice. And then part C. Suppose each child ticket cost $15 and each adult ticket cost $25. Compute the mean and standard deviation of the total amount spent per purchase. Ooh. Okay. We could do this. I can't use the answers from part B though. Yeah, I don't think I can use the answers from part B. Okay, let's do this. I'm gonna have to write out a couple things down here. This will be the last problem I do today, by the way. I can't use the answers from part B because that's combined children and adult. And they cost different amounts. Okay. So $15 times the mean of a child plus $25 times the mean of the adult should give me the expected value of cost on average. 15 plus 50. Why am I even typing that out? $65. That should work. For expected value, it's pretty straightforward for the mean. On average, there's about 1 child ticket, so $15. And on average, there's 2 adults, $25 per, $65. For standard deviation, this gets a little dicey, to say the least. Well, let's figure it out piece by piece. First, if I were to figure out the child standard deviation, multiplication does affect standard deviation if I'm multiplying each data point by the same number. So it does affect it. If it were addition, subtraction, then I wouldn't be able to do this. So for the child one, it would be 1 times 15, which is just 15. And for the adult, it would be 1.2 times 25. And then in order to combine them, I would have to square them to variance, add them together, and then square root back. Oh, this is weird. Okay. So for the child, 1 times 15 would be 15 for the standard deviation. zoom in down there. And for the adult, it would be 1.2 times 25, which is 30. So those would be the standard deviation of costs. Then I need to square them, then square root them back after I add them together. 33.54. Yep. That is exactly what I needed to do. That's a weird problem. They had me do that thing in part B, but then they didn't even have me use any of those answers in part C. I had to do something separate in part C. Huh. That's strange. Okay. Now, as I said, we are going to be continuing this on Friday. There's 1, 2, 3, 4. There's 4 more problems in the free response that we are going to go over on Friday. I am also going to be assigning you a practice quizzes. Again, I want to emphasize practice. This is going to be a practice quizzes, does not count against you, in regards to midterm practice. I want you to get that done. I'm going to assign that before I leave here today, probably by like 4th period when I have a break, because I don't have a break till 4th period. But I'm going to assign that by 4th period. Hopefully I have that whole thing lined up on quizzes. And then I want that done before Friday, because then on Friday, I would like to review the questions that we need to go over. In regards to the free response questions, you have the answers on that PDF that I provided for you, so you can review that thing at your own leisure, and then we'll kind of go from there. If you did not leave a comment in the chat, please make sure that you have done so. Otherwise, I am going to be signing off because the bell is going to ring in about 30 seconds, and I got to go get a couple things prepped for the rest of my day. So, yay! I don't know. Have fun. Enjoy yourselves. Take your stuff with you. Don't crowd in the hallways. I have no idea how next week is going to run. But whatever. Okay, bye-bye, bye-bye, bye-bye. Bye-bye. I don't want to limit that. Bye-bye, bye-bye. Okay, bye-bye. Bye-bye. I'm going to sign off.